The next major topic in this section is the null space of a matrix. So if you're given some matrix A, the null space of A is just the set of all solutions to this equation here, A times x equals 0. You can think of that also as if you wrote an augmented matrix where you put A in here for your coefficient matrix and then you put a bunch of zeros on the other side. It's all the solutions to that. And it turns out these solutions form a vector space. And that vector space is a subspace of R something. We can work out what that is by this. Let's say you've got AX equals 0 vector. Now A here, if that's m by n, x has to be an n by 1, and this over here is going to be m by 1. So we're talking about all the vectors x that are solutions. So these are vectors that are n by 1 vectors. So that's going to be a subspace of Rn. And the dimension of the null space is called the nullity of A. And one other thing I should have mentioned here is for all matrices, rank plus nullity is equal to the number of columns. So sort of the big thing we're going to do here is learn how to find a basis of the null space. But before we do that, I want to just play around with a matrix. So this example I've got here says the null space of this matrix has this basis. So let's play with that, and let's use octave to do it. So I'm going to put in the matrix, I'm going to call it A here. A is the matrix 2206. And the second row is 4411. And I'm going to call these two little vectors over here, I'm going to call them B1. Now, they're written as points, but we're going to make them columns. So that's going to be -1, 1, 0, 0. And B2 is the other one. -3, 0, 11, 1. All right, so if I take A and multiply it by B1, that should give me the 0 vector. Sure enough, it does. If I multiply it by B2, that also gives me the 0 vector. And if I would multiply it by any linear combination of these, if I were teaching this in person, I would ask people for random numbers from the class. But since I'm not, let's just put in, I'll pick a random number. Let's say 5 times this one plus, let's get crazy, 3.7 times that one. It gave me a star. What does that mean? It means a round off error. But yeah, it's giving me 0, 0. So yeah, anything we put in there will give that to us. And just for fun, let's do one of them by hand. If we take the 2206, if I take that down here and I multiply it by, let's just pick one of those two basis vectors, -1, 1, 0, 0. If I multiply this out, it's going to give me 0, 0. Now let's see. But remember, we'll take each of these and multiply them across there. So we'll get, for the top row, we'll get -2 plus 2 plus 0 plus 0. For the bottom row, I get -4 plus 4 plus 0 plus 0. So sure enough, this gives me 0, 0. So that's just kind of playing around with it. Next up, I want to look at how to find a basis. Just note, what does it say? Oh yeah, if you have an equation like this where you've got a 0 on this side, it's called a homogeneous equation. So this is a homogeneous vector or a matrix equation. If you write it out like this, it's a homogeneous system of equations. And let's find a basis of the null space of a matrix. I want to find a basis of the null space of this. And the way we do that, it's very similar to just solving this system up here. Ax equals 0. It's very similar to just solving that, but then at the end we're going to pull some vectors out. So rather than write out the technique, I'm just going to solve this. So what I'll do is I'm going to form the equation Ax equals 0 vector. And I'll actually write this out. 1, 1, 3, 2, 0. 2, 5, 11, 1, 0. Right, and then I'm going to row reduce that. Now, one thing you can look at here, you can say this is definitely going to give us at least one free variable, because it'll actually give us at least two, because this matrix, when you row reduce it, it's only got room for two leading ones. So we'll have at least two free variables. But let's row reduce it. Let's see, m is 1, 1, 3, 2, 0. And 2, 5, 11, 1, 0. All right, when I row reduce it, I get some fractions. So let's write it down as 1, 0, 4 thirds, 4 thirds, 3, 0. And then 0, 1, 5 thirds, negative 5 thirds, negative 1, 0. All right. So we're going to take this and write it out as a general solution, or parametric solution as we've been calling it. I'm going to give these variables some names. I'm going to call them x, y, z, and w. When I write out the solution, that top line gives me, well, first up, notice here's a leading one, here's a leading one. So both of these are free variables. So the top line of this matrix gives me the equation x equals 0. Actually, I'm not going to write the 0. I'm just going to move the z and the w across. So I'll get minus 4 thirds z minus 3w. Y is going to be 5 thirds z plus w. Then y and w, or I'm sorry, z and w are both free variables. And it's important here to write this out. Z equals z and w equals w. It's important to write those out and to put them in the correct order. Because now, what I can do is essentially think of this as being this times, well, I'll write it out since this is the first one. We're going to break this into x, y, z, w as a matrix, as a vector equals z times negative 4 thirds, 5 thirds, 1, 0. That's coming from over here. You can write this in as z plus 0w and then 0z plus w. So I'm really just pulling these coefficients out. Plus w times negative 3, 1, 0, 1. So my basis of the null space is just these two vectors. I'm going to write them as column vectors. So we've got negative 4 thirds, 5 thirds, 1 and 0. Then negative 3, 1, 0, 1. So that's the basis of my null space. And I'd also say my nullity here is nullity is the dimension of the null space. And so that's going to be 2. And before I stop this, I'm going to rewrite this one, negative 4 thirds. So that's our answer. And if you wanted to, You could scale this vector here. You could scale it by 3 and get negative 4, 5, 3, 0 if you wanted to get rid of the fractions. All right, I want to do more examples, but we'll save those for the next video.